We have a total of 7 degrees of freedom. We've got 4 here, we'll have 3 degrees of freedom for air. Okay. Oh, very good. Is it working?
Yep, it's okay.
Thank you, Judy.
Okay, this is what we did last time. Now, conceptually, what does this look like? Maybe it's worthwhile to do this. Is let's assume that I have all my data in terms of the total sum of squares. And what I do, and that's in terms of that line. And what I'm going to do is I'm going to fit out the effects of the full model. So to say the full model effects explains this amount of the total sums of squares. So this is the reduction in air sums of squares due to fitting U, A, B, and A, B. Okay, so this little bit is what? This is the total sums of squares. Here's the model sums of squares. What's that? If I got my total information, I estimate the total sums of squares. What's this remaining sums of squares? There, right? Okay, but what I'm doing here is I'm removing, I'm partitioning this part. Okay, so what I'm going to do is I'm going to fit the model for, say, the reduced model, U, B, and AB. Okay, and now what's this little difference here?
Partial sums.
That's the partial sums of squares. Okay, this is the idea. So this bit here is the partial sums of squares. So it's the effect of fitting A after fitting mu, B, and AB. Right? So this would be air here, right? This part would be air, and this is this. Everybody see the idea? Okay, so that's all we're doing. Okay, so this is what this is the extra sums of squares due to A after fitting mu, B, and AB. Okay, so it's an important concept. Now, if you've had regression, then you've talked about this. If you haven't, this is very important for analysis of design experiments because the sequence of fitting is important in terms of the hypothesis we're testing. Okay, so let me just review what this sequential, just write it down again. Just sequential sums of squares are sums of squares that are obtained where the effects are fit in order as specified in the model. Are fit in order as specified in the model. So if you think of the model over here, here's the model, and that's the order of the model. I fit mu first, then I fit A after fitting mu, then I fit B after fitting A and mu, then I fit AB after fitting A and B. Okay? And so on. Okay, so that's sequential sums of squares. Now partial sums of squares is that each effect is fit last after fitting all of the other effects. After fitting all other effects. And of course, that's exactly what we're doing here. We're fitting the effect of A after we've removed the effect of all the other terms. Okay. Now, what's important about these sums of squares have different hypotheses that they test. You got to be careful. These different sums of squares test different hypotheses. Now, that's important. Right? Because science, what is science all about? We set a hypothesis, we go out and get data, and then we want to test the hypothesis. Well, Lord, okay, you know what your hypothesis is, you got to collect your data, you're using wrong sums of squares, and you're not just the hypothesis you're interested in. This is important. Okay. So let's talk about this a little bit. Questions on any of this? Okay, I'm going to have to erase this, but it's okay. Well, now it is okay. Everything's recorded, so you didn't need to ask you, right? So you just go back and look. So in the future, we'll just have these modules that you guys watch, right, on TV. I mean, what's the future of this distance in? I don't know. I think it's a bunch of hype. You know, I may be wrong, but it is so boring to sit in front of a television screen and watch these things. So, well, how can I use these? That would be good to give comments on that, too. But I think to me, this is the most effective thing. You don't understand, you go back and look at it, and it helps. Okay, so let's look at ANOVA to show what I mean about these hypotheses being tested that are different. So let's look at, I'm going to write kind of a ANOVA table here. Source, and I'll fit A, B, and A, B, and this is after I fit out the mean, so let's not worry about that. And then I'll have the error down here. Now our error degrees of freedom, of course in general, are N minus P, but in our example this is 3, as we said before. Now if I fit each of these for our simple model, I just have single degree of freedom for each. So I have 2 levels of A, 2 levels of B, and the AB interaction is 1. Okay, so let's look at the sequential sums of squares. The sequential sums of squares, I'm going to use my reduction notation, is the reduction of the air sum of squares due to fitting A after fitting mu. B is the reduction in air sums of squares due to fitting B after fitting mu and A. And finally, AB interaction is reduction in the air sums of squares of AB after fitting mu, A, and B. And then, of course, we have the air done, whatever these are. This is the air. Okay. Whatever the air sums of squares is, it's y prime y minus the total model sums of squares, right? Use my notation. Okay, now the important thing is, what are the hypotheses that are being tested? These two are not what you're interested in generally in experimental sciences. They're not what you're interested in. What are they? These hypotheses for both of these depend on cell sizes. And really what they are is they're tested the quality of weighted means. Okay, weighted by your data. Now that might be right to write these out. I'll let you go see. It's in Millikan and Johnson chapter 10 if you want to look this up to see these. See Millikan and Johnson chapter 10. And I think that's the new one's electronic resource on the library. You can just look at that if you want. Okay. Well, what your hypothesis here is you're letting the number of observations in each cell be in the hypothesis. Well, wait a minute. This whole violates the whole idea of what science is, usually from an experimental scientist point of view, is you start with a hypothesis, you collect data, you draw conclusions about that hypothesis. Well, if you don't know what your sample sizes are before you set the hypothesis, you don't know what the hypothesis is. Be careful about these, using these sequential sums of squares. It's really important. I can't emphasize that as much as I... Okay, let's look at the partial. The partial sums of squares are a reduction in A after fitting mu, B, and AB. The partial sums of squares for B is the reduction of air sums of squares due to fitting B after fitting mu, A, and AB. And finally, the reduction in air sums of squares due to fitting AB given mu, A, and B. All right. Now, one thing to notice is, look, these are the same. They're exactly the same. Type 1 and type 3 sums of squares are exactly the same for the last fitted term. Okay, so you can use partial sums of squares or sequential sums of squares if you know what you're doing. Now notice really what happens here. To get each one of these, I have to fit 3 different ANOVAs. I get one ANOVA fitting A last. For this one, I get another ANOVA fitting B last, and another ANOVA fitting AB last. There's 3 really ANOVAs here. This is really not an ANOVA table. But you have to do this if you want to test the right hypotheses. What are the hypotheses here? Anybody know? I assume that you've talked about this in your previous classes. I hope you have you? Has anyone seen this description of this before? Okay, so you've all had design experiments class, right? And so you've never talked about the difference between partial and sequential sums of squares. No? I'm going to teach 802 next spring. You know. Anyway, okay. But academic freedom, okay. But I think this is important. What are hypotheses here? The hypothesis of A is the main effect, or the LS mean for A is equal for the first level of A is equal to the LS mean for the second level of A, and all the way up to the LS mean of the 8th level of A. Now, simple example, there's only 2 of them, right? Okay, so really, in our example, it's only mu1 is equal to mu2. But in general, I'd have A minus 1 degrees of freedom here, right? If I have A minus A levels, then those are all going to be equal. Well, that's hypothesis you're interested in. Equality of all LS means, okay? Population LS means. The same with this one, except it's for the B level. So this would be B1 equals mu bar dot 2 equals mu bar dot B. And of course, the hypothesis here is the no interaction. Right? And what no interaction is of course, mu ij minus mu I prime j minus mu I j prime plus mu I prime j prime for all ij. And it's just like all these little differences. We talked about what those are. Those are just little differences between the treatments. So all possible little differences you're testing. That's all interaction really is. These are the same. There's no interaction over here. These are the same hypotheses. There's some sums of squares that got to be the same. So if you're using a sequential sums of squares processor, you're using a regression processor that doesn't do this stuff, then you have to go back and just fit the model multiple times. So what? That's not hard to do. Okay? In fact, you're doing Excel. You can do those in Excel. You think this is in Excel, doing partial sums of squares? No, but you can do it. In fact, there's add-ons in Excel. You can do a lot of good statistics. Okay, with just Excel. But I don't think there's the issue. You know, they don't fit partial sums of squares. I assume it's all sequential. But maybe they do. I don't know. You know, it doesn't make a difference. You can do this. Okay. So I'll say no in passing. Why do we want balanced designs? No, when the data are balanced. From a data analysis point of view, then the type 1, this is type 1 sums of squares. Sequential are type 1. And these are type 3. Okay, you'll see another notation, type 1 and type 3. This is probably more common. Okay, it's not very descriptive, but when you say partial, it actually has some meaning to it. The type 1 sums of squares is equal to the type 3 sums of squares. When the data are balanced in this particular case. In a situation where all the cells are filled, okay, and every cell is balanced, then the type 1 sums of squares are type 3. That means it doesn't make a difference. You don't have to worry about this issue. These are always the same. The type 1 sums of squares are always equal to the partial sums of squares. Okay. And when you take the linear models will prove this. It's not too hard to show. Talking about orthogonality and stuff. But so it's an important issue. So questions about this? All right, I've got a handout. I don't think I'm going to. I've got a handout which is on the computational stuff. Do you want me to talk about that? I'll just pass this out. It's SAS. I mean, I put it on the screen if you want me to talk about it. Most people have used SAS to analyze data like this, right? Or R, right? Okay. Maybe it'd be worthwhile to talk about some of the issues here. I'll just stop. Your computer needs a restart. Oh, great. Oh, well. I didn't get to the good part.